Okay, previous lecture we looked at the jet engine, and this was trying to provide an example of how you use the steady flow energy equation, and we did this by comparing it to the closed cycle Brayton cycle that we looked at using a system-based approach. So this lecture we're going to look at actuator disk theory, and this is a nice way of using mass, momentum and mechanical energy conservation as expressed by the Bernoulli equation to examine propeller performance and also turbine performance, and try and use fluid mechanics to try and use to come up with a sort of a design protocol for designing propellers and to predict what they will be able to do. So we're going to do two lectures in one. We're going to look at propellers and turbines, and the easiest case is effectively a turbine because our turbine is fixed in space, so we can draw a control volume around it and we have flow going through our stationary control volume. So that's our control volume is fixed in space, and in the propeller case, effectively our propeller is moving through still air. Normally it's attached to an aircraft or a ship. So if we want to do a control volume based analysis with a propeller, we have to change the frame of reference and take away the propeller velocity from the propeller and also from the fluid around it. What this does, this places the propeller in a stationary frame, and the wind flows across the propeller, and effectively the propeller becomes in the same frame as a turbine. And then if we can do that, we can analyze propellers and turbines using the same bit of maths, and we can describe the characteristics of both of these systems in the same way. So that's what we're going to do. So we're going to take a propeller case as our sort of example, and we're going to describe it in a stationary frame, so it's a bit like a turbine. And we link these two things together using change of frame of reference. So, propellers are quite complicated. It's a three-dimensional flow. It's viscous because we've got boundary layers forming. There's rotational momentum, and we're not really interested at this stage in that complex flow. So what we do is we treat our propeller as a black box, more specifically as a thin cylinder. So our thin cylinder becomes a control volume, and we look at what goes into that control volume and what comes out of it, and the differences in the velocity and the pressure across that control volume are caused by the physics inside it, which is the propeller or the turbine. Okay, so this is why it's called an actuator disk theory method. So let's think about what is going on inside or across our disk. So our disk has a cross-sectional area, has diameter of the blades is d, and we can assume that there's a certain velocity going into the disk and a certain velocity going out of the disk, and effectively this is a cylinder, constant area, and given that the density is the same as the area are the same, that means that U1 must be equal to U2, and there's constant velocity across our actuator disk. And if we then said, well, let's apply momentum conservation to our disk, then we have momentum out minus momentum in equals the sum of all the forces. So we know that the velocity is the same across both faces, and we know the mass flow is the same across both faces. So the net momentum change across an actuator disk is zero. So that means that the sum of all the forces must be zero, and there are two forces. There must be a pressure difference, and there must be a force created. And there must be a force created because there's a force on the propeller that makes the aircraft move. So this force must be created by this pressure difference across the propeller. Okay, And just another point about where and when you can't apply Bernoulli. We can't apply Bernoulli across the station 1 to station 2 because it's a viscous flow, and we said that there are no viscous losses in our Bernoulli equation, so we can't actually apply it between those two points. So just to sort of explain this slide, this is our actuator disc, and we've got flow going through here. So effectively what we can do is we can say that this area is part of a stream tube, and this stream tube gets projected upstream and downstream. So all the mass flow going into this stream, into the entrance of this stream tube at this far upstream location, goes through the disc and comes out the other end. Okay. So let's think about what's going on in the far field, and how can we start to link this to what's going on across the propeller. So what we can do is we can apply the Bernoulli equation between 0 and 1 because there's no walls here, and we can treat the fluid as inviscid in these locations and this location. So we can apply Bernoulli equation between 0 and 1 and 2 to 3, and we can also assume that the pressure far upstream and far downstream is atmospheric pressure. So we can write the Bernoulli equation for stations 0 to 1, and that's what we've got here. This is the conservation of mechanical energy, and the same again from 2 to 3. And then there's nothing to stop us mathematically from adding those two equations together, so that's what we've got here. And then we can simplify this equation and knock out some terms that are equal. So for instance, we can knock out the atmospheric pressure, and we can knock out the U1 squared and the U2 squared, because these two velocities are the same because they're either side of the disk. So what we're left with is an expression for the pressure drop across the disk in terms of the kinetic energy difference between the far upstream and the far downstream points on our stream tube. So we know that the force on the disk is the pressure difference times the area. So this gives us an expression for the force, or the thrust if you like, on our propeller or turbine, and it's proportional to the square of the diameter and the difference in the kinetic energy between the upstream and the downstream. So that's quite interesting. So that tells us that if you want to create more thrust, the best thing to do is to make your turbine bigger. So every time you double the size of your turbine, the thrust that you generate goes up by a factor of 4. And your thrust is also a function of the difference in the kinetic energies between the upstream and the downstream. Okay, this is not the speed. This is the difference between the upstream and the downstream. Okay, so we can also there's nothing to stop us from drawing a control volume around the whole thing, and then doing a momentum balance on that particular control volume. So that's what we do here. We do a momentum balance between station 0 and station 3. We write out our momentum equation, which is this thing here. So in this case, we've got constant mass flow going all the way through, and in this case, U0 and U3 are different. So there is a flow, there is a momentum defect across this control volume, and that momentum defect generates the thrust on the control volume. And the only thing generating the thrust in the control volume is the propeller. So we have another expression for the force on the propeller. So that's quite interesting. So we've got this equation here, which this is the force on the propeller due to control volume across the whole thing from 0 to 3. And we've got another expression for the force, which is from Bernoulli. We got this from the previous slide. So both of these are right. So what that does, that gives us both of these are the same, So we can set these two things equal to each other, and this gives us a constraint on how U1 and U3 and U0 are related. And what it says effectively is this expression must be true, and that U1, the velocity on the blades, is equal to the average between the upstream and the downstream velocity. So this tells us that half of the speed change, and if you think about the force on the propeller, this speed change it generates the thrust. Half of this speed change is due to what goes on upstream of the propeller, and the rest of it is due to the speed change downstream of the propeller. So we can play around with a little bit with the force derivation, and we do this so we can look at the comparison between power and efficiency. So we know that our force from the large control volume is this, and we know that the mass flow through the propeller blade is this, and we've also found out this constraint. So we can do a little bit of maths and repackage the force in terms of velocities, in terms of the propeller velocity and the upstream velocity. And in particular, what we're interested here is 1 minus U0 over U1. Then if we want to start working out the efficiency of a propeller, we need to think about what we want, so what's useful, and what's useful is the thrust that we generate, so that's F, and the speed at that the aircraft is going. So remember that we did our frame of reference change, and the propeller speed was transformed into the speed of the air hitting the stationary propeller. So the free stream velocity, this U0 in the propeller case, this is the speed of the aircraft. So if we've got the thrust times the speed of the aircraft, this is what we're actually getting out of our propeller. This is the thing we want, and the power that we're consuming is the thrust multiplied by the speed at which the air is actually going through the propeller, and that's F U1, and we can write that here if we wanted to. Okay, so if we wanted to work out the efficiency, that's just the ratio of these two things. So it's FU0 divided by FU1. So that gives us our efficiency is actually the difference, or the ratio, between the upstream velocity, U0, and the velocity on the propeller blade. So this gives us quite an interesting relationship between power and efficiency. So we've got this curve, this graph here, so we've got efficiency on the y-axis on this side, and so this curve here, this arrow is the efficiency curve, and this curve is the power curve, and this is goes to the right hand side here, and the this is the ratio between the free stream velocity and the velocity on the plane, on the at the propeller. So what this tells us is when U0 over U1 is equal to 1, we have perfect efficiency, but we're not drawing any power, or we're not adding any power to the propeller. So what's happening is that the streamlines going through the propeller are parallel, and there's no compression of the streamlines. So U0 over U1 is 1, and we don't add any power. So as soon as we start extracting power, our streamlines converge to the propeller, and our efficiency reduces. So when you're designing a propeller, you have to start thinking about what do you want? Do you want a powerful propeller, or do you want an efficient one? If you want an efficient one and you want to generate a certain amount of thrust, the best way to do that is to make your propeller blades as big as you can. They will generate your thrust, and then you don't need to run it quite as hard, and you can run it with U0 over U1 nearer 1. Okay, so this linear line is our perfect line. In reality, we have to deal with some losses, and that's what this curved line comes from, and we're going to talk about that in the next slide. So in real life, we have some losses. So one of the losses comes down to the viscous dissipation of energy on the blade surface. So we're going to talk about that a lot more in the next few lectures. And when axial or linear momentum goes through a propeller, some of that energy gets converted into rotational momentum. And that rotational momentum doesn't do anything for us in terms of power transmission. So that's kind of lost energy that we have to treat as a loss. And also we've assumed that the pressure on our disc is uniform, and in reality it's not, because our propeller blades are turning around and the tips are going much faster than the parts of the blade near the axis. So this gives us pressure fluctuations or variations on the surfaces of our control volume, and that gives us an inefficiency. So that's a kind of a very qualitative explanation without getting into too much detail. And the way we can sort of deal with this is we know that the power, the lost power, if you like, P loss, is proportional to the mass flow going through the propeller, multiplied by the speed at which the flow is going through the kinetic energy that the flow is going through the propeller. So it's proportional, so we can assume it's linear, and we have a constant that we would have to do a measurement for a particular turbine to work out what this C constant would be. And if we have this kind of relationship, effectively we can transform our actual propeller efficiency into an equation that looks like this. So what we've done is we've added the lost power onto the power we have to burn to generate this thrust at this aircraft velocity. So this is the power consumed by the propeller, and this is the additional power that you need to deal with all of these losses. Okay, and you get to a typical efficiency of about 0.85, so in reality, a propeller is quite an efficient way of generating momentum, or generating force and thrust. Of course, so compared to a jet engine, it's very inefficient indeed, although we have to remember with a propeller you have to attach it to a heat engine, and that might only have 50% efficiency or so. Okay, so that's propellers. So turbines we have to treat slightly differently, because our efficiency has a slightly different definition. So most of the actuator disk theory conclusions, which are these key ones here, these things apply to turbines. So so in particular, F proportional to D squared. This tells you why turbines just keep getting bigger and bigger and bigger. So people come up with new manufacturing methods and new materials, so you can generate very light but very large and strong turbine blades. So when we talk about efficiency of turbines, we're interested in extracting energy. So the amount of energy or power that we have at the turbine blade is the thing that we're after. So we generate a certain amount of force from the pressure difference across our turbine, and the amount that we can extract is the velocity of the fluid at the turbine blade, which is U1. And the amount available that we've got is effectively the force multiplied by the free stream velocity. So this is the amount of kinetic energy per unit time that the turbine is going to be exposed to. So that's F U0. So you end up with an equation that looks like this. an equation that you can manipulate to end up looking a bit like this. Okay, so this is not really important. I'm not going to ask you to derive these kind of things. So when we plot this curve, we end up with something that looks a bit like this. So the x-axis in this plot is u3 over u0, so that's not the same as a propeller. So u3 over u0 is the difference between the upstream, the ratio between the downstream and the upstream flow velocities, and r of x is the efficiency. So that's this perfect efficiency. And when you plot this curve, you end up with this red line, and you get an optimum. You get a maximum efficiency when u3 over u0 is about a third, and this gives you an efficiency of around about 60%. So the maximum theoretical efficiency that you can get out of a wind turbine is 60%. And then we have to deal with fluctuating winds, directional changes. You have frictional changes, frictional losses on the bearings. You've got mechanical losses on the gearboxes, and then you've got electrical transmission losses on the high voltage side. So it's still reasonably efficient compared to a heat engine, and wind is effectively free energy, but it's not perfect, and there is a limit on what you can achieve. Okay, so got to the end of the lecture. So actuator disk theory is a nice way of looking at mass and momentum and Bernoulli, and we have to be careful about where we can apply the Bernoulli equation. We've looked at how changing the blade size can change the force and therefore the power output, and we've looked at the efficiency of propellers and wind turbines, and they have some useful characteristics. And reading wise, Crow doesn't have anything on actuator discs, but Sengel and Simbala do. If you want to read that, this is an old edition, but I'm sure the newer editions will have something in there as well. So you can. This is a nice way to reinforce material that is in chapters 9 and 10, and have a go handing in 10.4.